Okay, so let us start. So what I am trying to, in the last two classes, we have just discussed some experiments and some issues in the field of quantum mechanics. That is just to get an idea as to what are the important aspects that we have to keep in mind when we learn quantum mechanics. Okay, so the central aspect of quantum mechanics here seems to be that we have to deal with something called what Eddington called a Wavicle. Okay. So in the name suggested by Eddington, so this is our central issue. It's so something called a Wavicle, and how does it look like? We do not know how does it look like, but so let's say that how does it look like is probably not a good question to ask. But then, if you believe that it should look like something, then there is one form which I think many of us see very often is something like, okay. So does it look like this? Nobody knows, but this is something which everybody imagines that it might look like this. Okay. So what I am writing here is just a one dimension. So basically, we have an important misunderstanding or lack of understanding here, that we do not know how does it look like. But the whole point is that it doesn't matter actually. Or how does it look like? If you are not able to answer that question, it doesn't matter. You can still make some progress. So we can ask a question that how do we represent it mathematically? Represent it mathematically. Okay, so this is probably a better question to ask, and we will go by our experience. Classically, a wave is represented by a function of both space and time. Both space and time. And for simplicity, let us work with one space, one time. That is 1 plus 1, we call it. No, one space, one time. So in which case, okay, so in which case, a wave is represented by some function of f of x comma t. That means we cannot simply talk about a function of t or 1x, something like that, because a wave is something which we are familiar with waves of this type. So there is a wave like this. So there is going to be a function f of x comma t which will represent this wave. And we are familiar with that this f of x comma t, okay, so this function or the wave f of x comma t satisfies satisfies what is called a wave equation, because all classical waves that we know will satisfy what is called a wave equation. Now, what is this wave equation? The wave equation is something like this. In one space, one time dimension, let me write it. So del square f by del x square minus 1 by v square into del square f by del t square is equal to 0. And here, of course, this v is the velocity of the wave propagation. Now, once you say that you have got a wave, okay, so we are working with a premise that even particles have wave nature. Waves anyway have wave nature, but particles have wave nature. Now, the moment you say you have a wave, it is described with lambda, the wavelength, and the frequency nu. Okay, these two quantities are important properties of a wave, and these two properties can also be represented by two related properties. For example, you can say there is something called k, which is equal to 2 pi lambda. Okay, so this is a property related to lambda, and there is a property called omega, which is called angular frequency, which is 2 pi times nu. Okay, so we can work with either lambda and nu or k and omega. Okay. Now, suppose you have a wave like this, a simple wave, which can be written in terms of, so suppose I want to write this wave. Okay, so mathematically, this wave can be represented as some f of x comma t. You can write it as some kind of an amplitude, which I will call it as a, and then you can say there is a sine or cosine of, so you can say 2 pi by lambda into x minus 2 pi by omega, 2 pi by t into, okay. So what does that mean? That means that by the way, when we write a wave like this has the following property. That is, f of x plus lambda and t plus capital T is equal to f of x. So that means there is a spatial periodicity defined by the wavelength, and there is a temporal periodicity defined by the time period. And the relation between time period and frequency is 1 by nu. Okay, or if you write down this one, this is basically equal to 2 pi by omega. So I can write in terms of, so using this k and omega, so you notice that this particular term can be replaced by k, and this particular term can be replaced by omega, and then you can write down this f of x comma t as a sine kx minus omega t. A sine kx minus omega t. And we are familiar with waves of this type. Okay. Now you can say that if, for example, this yeah, so this is just a classically we represent this wave like this, but sometimes what we do is we try to represent. Okay, so we represent for kind of a for mathematical ease. Okay, for mathematical convenience, or ease, f of x comma t has some a into e to the power I kx minus omega t. Okay, so that the imaginary part of this will be this, or real part of this will be this. So you can work with this one, and finally you take a real part or an imaginary part for interpreting the results. So this is something which we are familiar. So it is more convenient to use this form than the trigonometric functions. So because of that, we sometimes use this, and we call this so in 3-dimensional, in 3D. So this has the form like this. It has the form given by some f of r comma t. It is given by some a into e to the power I k dot r. These are vectors. K is a vector, r is a vector, minus omega t. Okay. Now, so you can say that if f is a complex number, then you can think this as a complex number can be written as some modulus and then some phase. Okay, so suppose if I say that the phase is fixed. Okay, a constant phase. That means if I say that k dot r, for example, let us fix it to be minus omega t. Okay, is equal to 0. Let's say, implies that r dot k is equal to omega t. Okay, so for a given time, for a given t, this r dot k is equal to constant. Correct? So r dot k is equal to constant is an equation of a plane. Equation of a plane. Now, that is, if you ask what is the locus of points r such that for a given k, r dot k is constant, is a plane. Okay, so that means the constant phase. Suppose if you say what is the locus of points with the phase is constant, and that's a plane. And this plane, where is this plane? This plane is equal to constant. So that means this constant determines the location of that plane. Now this location will change as a function of time. So the constant phase plane will actually travel, okay, as the wave is propagating. Okay, so now you can see that if you ask this question, that so since this is the equation of a plane, so we call this a plane wave. So this is what we call as a plane wave. Okay. So a typical wave it can be represented as a plane wave. So what is that the plane wave has? Plane wave has its wavelength. There is only one wavelength, which is given by 2 pi by modulus of this k, and it has frequency, which is uh, 2 pi by omega. That's the time period. So these are the two things. So a plane wave is basically a plane wave expression. This a into e to the power I k dot r minus omega t is used only for representing a wave, mathematical representation of a wave. Okay. So we can conclude that whenever we have a wave, okay, so a wave with a given wavelength lambda equivalently 2 pi by k and a given time period which is equivalent to 2 pi by omega can be mathematically represented by a plane wave. So let me write this in one space, one time dimension. F of x comma t is equal to a into e to the power I kx minus omega. Now, just 1 minute. Oh, sorry. Okay. So now what we have, so we have this plane wave, and we can define here that if you say that constant phase points, that is kx is equal to omega t, okay, and x and t are variables here, okay. So this implies your dx by dt will be equal to omega by k, and this is sometimes you define it as velocity of the wave. Okay, so dx by dt is equal to omega by k is the velocity of the wave. So if you know the frequency and wavelength, we can always find out what is the velocity of the wave. Okay, so the important point is that whenever we have a wave with a given frequency and wavelength, we will represent that wave mathematically in this fashion. Okay, so now we can say that okay, this is a wave, and this all waves should satisfy what are called a wave equation. Okay, this is a solution of wave equation. Now suppose if I substitute this in the wave equation. Okay, so why am I interested in describing a wave here? Because we have this, you know, that this French physicist called Louis de Broglie in 1923 has has shown that a particle has wave nature. Particle has wave nature. Okay, so he simply looked at electromagnetic radiation, which has a particle nature from Einstein's theory. We have discussed that earlier. So particle has wave nature, and he said, okay, so you have a particle, so energy and momentum are the properties of the particle. So these are particle properties. And so frequency and lambda, these are wave properties. Okay, and in the first 25 years of quantum mechanics work, has established a relation between these two. So first relation comes from the Planck's hypothesis that E is related to h nu, and this is what tells you waves can be understood as particles. And de Broglie relation tell you this P is equal to h by lambda. It is this h which actually connects these two things. So that is why Planck's constant is very, very important, a very important fundamental constant. So the wave sector and particle sector, which we consider them to be two different sectors, can now be said that they can be interchangeably, they are one and the same, because every wave is a particle, every particle is a wave. So this is de Broglie wavelength. That means if you have a particle with some energy E and momentum P, we can consider that as a wave with a wavelength lambda and frequency nu, where the relation is given by this factor. So now that we have this case, so we can ask a question that how do I mathematically represent a particle? Now, particle earlier we used to represent mathematically by a point in the a configuration space or a phase space, right? So a point in the space, but now particle cannot be represented as a point because particle has a wave nature, so it will occupy some space, so it is spread in the space. So a point description is no longer valid here. So we have to represent it with a function of space and time, and because of that we will have to consider, so if you have a wave, whether it is a particle wave or a real wave, this is the plane wave is the right description of the function. Okay, so we have to represent a particle. Okay, so the conclusion is that even a particle has to be represented. Even a particle has to be represented by a function of x and t. Okay, because it has wave nature, and therefore a point in space, description is inadequate. Okay. Now, let's consider the simplest possible case. So let's consider a free particle. Consider a free particle. Now we know that free particle has got an energy of the free particle is given by p square by 2a. It has only kinetic energy. It does not, you know this from your Hamiltonian mechanics, the total energy of the free particle is p square by 2a. There is no potential. Free particle means it is force free particle. Okay, consider a free particle. Now, a free particle has fixed energy, fixed value of E, and it has a fixed value of E. There is a fixed value of energy and fixed value of momentum. That means this is directly related to some frequency and this is directly related to a lambda. So a free particle is the simplest particle that we can consider, which has got a fixed value of the momentum. That means there is a fixed value of lambda. Okay, so this could be. So now I want to represent this particular free particle mathematically. Then a function of x comma t represented as some constant a into e to the power ikx minus omega t. Okay, so e to the power ikx minus omega t is the right description for this, because here k is given by 2 pi by lambda and omega is given by 2 pi nu. So with this description, so this is the simplest case. So this is probably how a free particle can be represented. Okay, if there is a potential, maybe that force will try to do something to the particle, maybe there is a change in the momentum and all that. But that is why we are considering a simplest case of a free particle. So the claim that I'm going to make is, or the starting claim that I'm going to make is, that a plane wave is the right description. Okay, so let me write it here. A plane wave is a correct mathematical description of a free particle. Okay. See, the question that I asked here, if you look at this question, that what we represent, so we asked this question here, right? How do we represent a wavicle mathematically? So I am considering a free particle. Okay, it has a wave nature, but free particle has got a fixed energy and fixed momentum. Okay, and if I give some energy and momentum initially, that will not change. That is the meaning of saying fixed value of energy. Energy and momentum are conserved quantities. That's what I meant by saying this. So that means its wavelength and its time period does not change. So when a free particle moves, it is like a propagation of a wave with a fixed value of wavelength and a fixed value of time period. Okay, so a plane wave is a correct mathematical description of a free particle. Okay, so now if I if I say this, then since this free particle is also it is a wave, so so we may naively expect so we may expect, okay, so maybe let me add this naively, that it satisfies wave equation, because our experience has been that all the waves which we represented mathematically are satisfied wave equation. So now let's look at that. That means you have del square f by del x square minus uh, 1 by uh, 1 by v square to del square f by del t square is equal to 0. And let's substitute. So let's substitute our plane wave f of x comma t is equal to e to the power I kx minus omega t in this equation. So in the wave equation. Okay. Now, if you substitute, what happens? I have to do differentiation twice with x. Okay, so that will give me minus k square and minus 1 by v square, and I do differentiation twice, then I get minus omega square equal to 0. Okay, so that is what I will get. So this implies I get omega square is equal to v square k square, or this implies that omega is actually proportional to k. Okay, so we call this as dispersion relation. Dispersion relation. So we get a dispersion relation as omega is proportional to k. Now we ask a question that is this is this consistent? Is this consistent with quantum mechanics? So that is the question that we are going to ask now. What does that mean? We know that for a free particle, we know that energy is equal to E square by 2a. Of course, we have to keep in mind that we are talking about a non-relativistic case. Non-relativistic scenario. If you are taking relativistic case, then of course this is not p square by 2m. You will have a relation between E and P, which is more complicated. Okay, so note for relativistic case, we have E square is equal to P square C square plus M square C to the power 4. So we have to use this relation. But we are not going to do relativistic case. We are talking about non-relativistic. Now you can see that so quantum mechanics. What quantum mechanics tells you? It's not basically quantum. Idea of quantum or quantization tells you that E is equal to h nu. Okay, that means E is proportional to nu, which means E is proportional to also omega, correct? So you can say H into 2 pi or omega by 2 pi. Okay, so if I take this 2 pi here, then you write this as H cross omega. H cross is defined as H by T. So important thing to notice is E is proportional to omega. Now, on the other hand, if you take P, P is equal to H by lambda. Okay, P is equal to H by lambda. So let us say that I will divide this by 2 pi and then multiply this by 2 pi by lambda. And what is 2 pi by lambda? Is basically K. So this again is H bar into K. So this tells you P is proportional to K. P is proportional to K. Now substituting this one in this equation, okay, so we have E is proportional to omega, P is proportional to K, but our energy is equal to P square by 2A. Implies omega has to be proportional to K square. Okay, so omega proportional to K square is the correct dispersion relation, for a particle exhibiting wave nature. But we are not getting that one. Okay, so we are not getting that one. Okay, so now what to do? You can do two things. Okay, you can doubt maybe plane wave is not the correct description mathematically. But then what else? Because plane wave, if the moment you say you have a wavelength and time period, then this is the simplest wave that you can have. Only one only this mathematical expression is the one which you can use. Okay. Then what is the other option? The other option is you say that okay, maybe the wave represented or the wave representing the uh, quantum mechanical particle is not obeying the wave equation. Okay, so because this omega is proportional to k is a consequence of using wave equation, right? So this particular thing is because you are assuming that this will satisfy wave equation. Okay, so what is the possible conclusion? The conclusion can be from this exercise. So we can conclude that conclusion can be the following: that uh, the plane wave a plane wave description of a free particle is correct, but wave equation is not the correct equation to describe particle waves are matter waves. Sometimes it is written as matter waves. So this seems to be the only possible conclusion that you can draw. Okay. So now we can ask a question that now we are coming to a point where if the wave equation not the correct equation, but what is the correct equation? Okay. So the question is, what is the correct okay. Now we can heuristically think that our aim is to get a dispersion relation which is omega is proportional to k square. Okay, that is our aim. But so what is it that we are continuing? Okay, omega equal to with a plane wave. Plane wave describing a free particle. Now, notice that now you stare at this equation, that is your f of x comma t is equal to e to the power I kx minus omega t. You stare at this equation, you want to get omega and then k square. That means your equation, okay, so to get omega proportional to k square, okay, we should have single time derivative and twice space derivative. Single time derivative and twice space derivative. So let us propose that there is a equation which is let's say del f by del t, okay, and let's say on the other side you have del square f by del x square, okay, and let's say there is some proportionality constant, okay, we can say this is proportional to this, and let's write some proportionality constant to be some kind of a constant c. Okay, so this is our okay, so let us propose this equation. Okay, so now substitute f of x comma t is equal to a into e to the power I kx minus omega t in the proposed equation. new equation. Then what happens? I have minus I omega. Of course, you have a into e to the power I kx minus omega t, I kx minus omega t is equal to c into minus k square a into e to the power I kx minus omega. Okay, so this is something which is not zero, so we forget about this. So I will have I omega is equal to c k square. C is a constant. Remember, c is a not it's not velocity of light. So c is a constant. So we have this dispersion relation, but of course we have a required dispersion relation. But then we have to fix the c. Okay, so this is a required dispersion relation. But we need to fix C. The constant. So for fixing C, what we will see is let's go back to our energy momentum relation. So we have E is equal to P square by 2m. Okay. So that implies, so we have already said E can be written as h bar omega and P can be written as h bar k. So h bar square k square by 2m. Or in other words, our omega is equal to h bar k square divided by 2m. Okay, so comparing these two relations, okay, so comparing these two, we get C divided by I is equal to h bar by 2m. Or in other words, the C is equal to I h bar by 2m. I h bar by 2m. So we have fixed C. C is equal to I h bar by 2m. Okay. So now our equation, we can go back and then write our equation as, so the proposed equation is dou f by dou t is equal to I h bar by 2m into dou square f by dou x square. Okay, so this equation is something which we have come to by determining this one. Now, you know that as you can see here that now I want to see some correspondence between this equation. Okay, so I want to look for correspondence between this equation and E is equal to P square by 2a. These two equations. Now, why I want to talk about correspondence? Because in classical mechanics, we have this understanding that if you say, when we talked about canonical transformations, when if you consider time as a coordinate, a canonical momentum corresponding to time is E, correct? So, and suppose if x is a coordinate, canonical momentum corresponding to x will be P, right? So there is a conjugacy relation between P and E. So I want to recognize that an operator correspondence between this uh, energy and momentum variables and this partial differential equation. Now, one thing is that all these observables are properties. In quantum mechanics, any property will have a proportionality of this Planck's constant. Like we have seen, E is equal to h bar omega and P is equal to h bar k. Okay, and for example, L square, the angular momentum square, will be equal to h bar square into L plus 1. So there will be some. So L square is proportional to h square, P is proportional to h bar, E is proportional to h bar, like that. So the property, so basically what is that I'm trying to abstract the concept is that any property is proportional to h bar. Square of the property will be proportional to square of this h bar. Okay, so if I want to get that correspondence here, so what I will do is I multiply the above partial differential equation by IH bar on both sides. IH bar on both sides. So if I multiply that, then I will have IH bar into dou F by dou T is equal to minus h bar square by 2m into dou square F by dou x square. Okay. So this equation is satisfying the correspondence that I am looking at. Okay. What is the correspondence? This is P square by 2m. So P square is proportional to h bar square. This is E. So E is proportional to h bar. So from here, we can decipher, we can infer an operator correspondence, that whenever I have E, now this E has a correspondence to something called IH cross by dou T. And whenever I have P, P has a correspondence to minus IH bar dou x. Okay. So this kind of an operator correspondence can be inferred from this. Now, if we have such an operator correspondence, and then you go back to this relation and then put this operator correspondence in this, you will get this. Okay. So this equation is incidentally the correct equation, and this is what is called Schrödinger equation. Schrödinger equation for free part. Okay. So whatever I have, whatever this argument that I have used today to get this Schrödinger equation is not, so this is, so the argument, this I want to make it very clear, the argument used Here, to arrive at Schrödinger equation, is not a derivation, is not a derivation of Schrödinger equation. B, it is not the way Schrödinger obtained it. It is not a derivation of Schrödinger equation. It is not the way Schrödinger obtained it. Okay, so this is a simple, what we call as a heuristic argument. Heuristic argument. Okay, so you should not consider this as a derivation, and Schrödinger equation cannot be derived because Schrödinger himself did not derive it. So when somebody says derive Schrödinger equation, then we must say that okay, there is no such derivation. Okay, so I am not deriving Schrödinger equation. I cannot derive Schrödinger equation, as I told you, but it is a heuristic argument, a simple heuristic argument. Schrödinger did not derive it or did not obtain it in this way. He had a different approach. Okay, so but that is a little complicated. But right now, I am just presenting this heuristic argument so that we want to understand quantum mechanics as we are studying in 2021. Okay, so when 1926, when Schrödinger obtained this, the background and the knowledge available at that time was very different. So if you want to understand how Schrödinger did it, it's not that easy. It's quite tough. But nevertheless, it's interesting to understand how he has done it, because most of the times the original works are always very, very interesting. Okay, so this is one part, and now I want to make two generalizations of this. Okay, so first generalization. Okay, so two generalizations. First generalization is to a free particle. Okay, a free particle in 3 dimensions. So if you have a free particle in 3 dimensions, we are going to have our energy to be px square by 2m plus py square by 2m plus pz square by 2m. So there will be 3 components of the momentum like this. So correspondingly, we will have a Schrödinger equation like this. Okay, so let's say IH cross. So let us bring this character psi here. So dou psi by dou t. Now psi will be a function of r comma t is equal to minus h bar square by 2m. I will have squares like this. So this will be a Laplacian square, del square. So this is the Schrödinger equation for a free particle in 3 dimensions. So this is my first generalization. Okay, my second generalization is uh, a particle in a potential given by V of R. Now you know that energy is basically additive. Okay, just like here, and kinetic energy of first coordinate, second coordinate, third coordinate, as we are adding it, the energy is additive. So we are going to have our energy as px square plus py square plus pz square divided by 2m plus the potential energy Vr. Okay. So the Schrödinger equation corresponding to this will be IH cross del psi by del t. This will be r comma t is equal to minus h bar square by 2m del square psi of r comma t plus v of r into psi of r comma t. Okay. So this is the Schrödinger equation for a general particle in some potential V. So now we can ask a question that okay, maybe I can also uh, do one more generalization. Let's go back and then say that there are three generalizations. Three generalizations. That is, now I'm going to talk about uh, n particles. N particles. Okay. Now, if you have n particles, then I'm going to write down the Schrödinger equation in the following fashion. IH bar dou psi. Now, the psi will be a function of R1, R2, etc. Rn, comma t divided by del t is equal to sum over I is equal to 1 to n minus h bar square by twice mi, because each particle can have a different mass, del I square plus, let's say that each of them may have some kind of a potential. Okay, or I can write this as a potential R1, R2. Okay, so both interaction potential and also external potential, I will dump it in this P, which will depend on all these coordinates. So this psi of R1, R2, Rn. So this is the n particle Schrödinger equation. Okay. So this is a kind of a straightforward generalization of this thing, heuristic argument. Okay. So okay, so now let me try to make a couple of remarks. Okay, some remarks. Some remarks. So this psi of x comma t okay, is complex value function. Complex valued function. What does that mean? That means x is a real number, t is a real number, but psi of x comma t is a complex number. That means it is a complex valued function. That means for every x and t, psi has to be complex. Now it is easy to understand. See, for example, if you look at the Schrödinger equation, okay, so let's say IH cross dou psi by dou t is equal to minus h bar square by 2m into let's say del square plus some potential V acting on psi, let's say. Okay, I have used 3 dimension, but it doesn't matter. The argument is. Now look at the right hand side. So V is a potential which will be basically derived from the force, and this is a time derivative with respect to x, y, z. So these are all real quantities. And dou by dou t of some psi will also be real. Suppose assume psi is real. Okay, so if psi is real, this implies the right hand side of this equation is real, and left hand side of this equation is imaginary because it is multiplied with I. Okay, so that is something which is absurd because real and imaginary parts cannot be equal. They are linearly independent in the complex plane, right? So one way to have an equation like this itself is that the psi itself has to be complex. Then the real part is equal to real part, imaginary part is equal to imaginary part. That makes sense. Otherwise, by structure, that the Schrödinger equation, the psi has to be a complex valued function. Now, I also want to tell you here that if psi is not complex value, okay, so if so I do not know, if you don't understand this right now, you don't worry. So if psi is not complex valued, we cannot explain interference. Okay, so I want you to think about it. Think about it and see if you can understand why it is so. If not, we will work it out later. If psi is not complex valued, we cannot explain the interference. But interference is physical. We are observing it in experiments, and hence the only way of explaining the interference is by letting the psi a complex valued function. And I already gave you another argument here that it has to be complex valued so that you get this equation makes sense. Okay, so that is the first remark I wanted to make. The second remark is with respect to so what does psi x comma t represent physically? Now, this question might surprise you at this moment because we started saying that we want to represent a particle, and we took a plane wave. We said plane wave is a representation of a free particle. Then we argued that the equation has to be changed. Wave equation is not the right equation. Then we came to Schrödinger equation. Now we are asking this question again. What does psi represent physically? So you may ask, what do you mean by this? Doesn't it represent a particle? Or what tough particle does it represent? Even the question looks a little trivial and probably also not well placed, but this is a question which really has some deeper consequences. Okay, so let's say naively somebody says, okay, it represents a wave. Okay, so it represents a wave. Okay, now so there is some kind of a contradiction with this. For example, suppose you see people observed something called this particle tracks. Particle tracks in cloud chamber, for example. Okay, so this was initially done by Wilson and others. So Wilson's cloud chamber experiment, etc. So in cloud chamber, if you see those photographs, let's say you have something like this, and then you will see the particle going like this, and some particle coming like this. So this kind of tracks you can see. So now what happens is that if this is a wave and this is a wave, at this point when these two waves are meeting, we know how waves meet with each other. And waves meet, then there will be some constructive interference, destructive, so some overlap will be there. And then after that, the waves will not go as if they are particles. Okay, so particle tracks in cloud chamber look, appear as if the particles have no wave nature. Particles have no wave nature. So now, if this represents a wave, psi of xt, of course, all the experiments that we are talking about can be the results can be mathematically verified by using the wave function. Okay. But what is this wave function that represents of what property of the particle does the wave function represent? So this question is something which is very it is deep question, in the sense that there is not a very nice answer for this question. Now the second thing is that let us look at the generalization 3 that I have talked about. Okay, so if you consider a two-particle system, n particle you forget. So if you consider a two-particle system, then the wave function is basically psi of r1, r2, t. Okay, so if at all this represents a wave, the wave is not in physical. Wave is not in physical space. Physical space means the space of x, y, z. It's not in physical space, but in configurational space. Configurational space. What is a configurational space? For two particles, configurational space is a six-dimensional space. That is a six-dimensional space for two particle system. Now, what does that mean? That means whether this wave is so how is the particle for first wave? How is the wave for first particle? How is the wave for second particle? How do we understand these kind of questions? So even though this seems that this represents some kind of a wave, but this wave does not seem to be anything that we know. Like initially, some of you have asked a question: is it a transverse wave or a longitudinal wave like this? Now, this wave itself is something very strange. We don't know what kind of a wave it is. Okay, so this was a big problem when Schrödinger equation was written down to interpret physically what this wave is all about. Okay, so for example, let us slightly look at the history. In 1913, Bohr has explained hydrogen atom. Okay, so not Bohr, Bohr. So Bohr model of hydrogen atom has the following thing. So he said there are some orbits called stationary orbits. And if the electron is in the stationary orbit, it doesn't radiate energy. Now, how to find out stationary orbits? He said the angular momentum MVR will be nh by 2 pi. So this is the basically Bohr's postulate. Bohr said you find out what are these, find out the radius r such that MVR is nh by 2 pi, and that gives you stationary orbits. Electrons are in the stationary orbits, they don't radiate. But when the electrons go from one orbit to the other orbit, then they give radiation. That is what we observe as a line spectrum. All that was a great success. His hydrogen spectrum was very, very satisfactorily explained using Bohr model. But then this is still a postulate. Okay, that means why this should be a stationary state? Why this condition or why electrons should not radiate if the electron is satisfying this condition is something which he just postulated it. I mean, he had some insight and then he postulated it. But we don't know why it should be like that, correct? So then in 1923, when de Broglie postulated this, so de Broglie came up with this thing that P is equal to h by lambda, or lambda is equal to h by P. When we write de Broglie, we should write lambda equal to h by P. So when he came up with this one, then there was some kind of a picture like this. So let's imagine that you have a kind of a nucleus here, which is a positive charge, a proton, and then you have, let's say, an orbit which is, I did not draw the circle, so assume that this is a circle. Now, if this electron is like a wave, okay, so then we may try to represent this wave in this fashion. Okay. Now we ask ourselves a question that if this has to close onto itself, okay, so let's say that electron is stable in an orbit if the corresponding, or if the wave closes onto itself. Suppose if I make this hypothesis, then I know what is the condition because we are familiar with this in classical physics. Now you can say that, okay, the total circumference of the circle is 2 pi r, and 2 pi r has to be equal to what? Lambda, 1 or n lambda, the integral multiples of lambda. Then it will close onto itself, correct? Now let's come back to our de Broglie and say that this is equal to, so this is equal to n into h by p. So this gives me p times r, which is equal to nh by 2. So this condition, I can now understand why this condition is, because Bohr's postulate can be understood as a consequence. P is m times v, right? So p times r is the angular momentum. So the angular momentum is nh by 2 pi, is something which can be understood from the wave nature of the electron. So people like Schrödinger, Einstein, they actually felt that the electron in the hydrogen atom is a wiggly thing like this. Okay, so it is wiggling around this nucleus exactly in the, even though the picture that I drew is not very good, but it is this kind of a picture that these people had in mind. This electron will actually fluctuates around that orbit in this fashion, and that is why the Bohr's postulate can be understood as a consequence of the wave nature of the electron. So if you look at this, my second remark in the context of these expectations, my second remark tells you that it is far from reality that an electron is, suppose if you are talking about two electrons, now these two electrons, the wave function, which is the solution of Schrodinger equation, is not going to tell you any wave like this. Okay, so that is kind of a disappointment to Schrodinger, and he was in some sense kind of a complete fix, because he has a very successful equation, but he doesn't know what the solution is or what to represent physically about the solution. Okay, so this thing continued for quite some time during those times. Okay, so this is where an important contribution from Max Born comes in, and Max Born was so let's talk about Max Born a little bit. And Max Born, and before we talk about Max Born, we talk about a little earlier. So when Einstein had, so talk about Einstein a little bit. So Einstein, he showed that in 1905, he showed that E is equal to h. That means uh, electromagnetic radiation is basically a collection of light. We call them as light quanta, but later we know these light quanta are named as photons. The collection of photons. Okay. Now, every light quanta has got an energy h nu. Now, classically, suppose let's say you have some kind of a star here. So you have a star here, and then somewhere on the earth here you are observing. So this is our earth. Okay, so you are observing the starlight. Okay. Now what happens? Classically, the energy of radiation from the star falls falls as 1 by r square. Okay, energy of the radiation from the star falls as 1 by r square. So that means if your star is very far away, then you get a very faint, very low energy radiation. Okay, so this is something which we know classically from classical electrodynamics. We can show that this is the case. Now, Einstein had a difficulty to understand it from his observation. Suppose, let's say that a light quantum is emitted from the star. Okay, so let's say so h nu is emitted from the star. Okay, and let's say that this is some kind of a red photon. That means the nu is corresponding to red wavelength, red photon. Now, when it reaches, okay, so it is observed. It is observed on the Earth. Also as a red photon. That means this falling of energy is not happening at the level of photon. If a red photon with energy h nu is emitted, we are also receiving it on the Earth as a red photon. So no, so there is no reduction in energy at a single photon level. But it is also true that classically energy is falling as 1 by r square. So Einstein had the following argument. So let's say that you have a star here, and let's say at some distance from the star, you have a surface of a sphere. Okay, surface of a sphere. Now the surface of a sphere goes like 4 pi r square, right? It is 4 pi r square. It is equal to 4 pi r square. Now, as r increases, the surface area goes like r. Surface area of a sphere will increase like r square. Okay. Now, if certain number of photons have emitted by this star, and as you go, this number of photons have to be distributed over the entire surface. Correct? Now, let's say we have a detector here. Let's say I have a detector here. Okay, so it has some small detector cross section, right? So we have some detector kept here. Now, as r is increasing, because the number of photons have to be distributed isotropically throughout the entire surface of a sphere, then the number of photons that will reach my detector will fall like 1 by r square, because since area is going like 1 by r square. Okay, so he defined something called P of r, okay, which is the probability of a photon reaching the detector. And he argued that this P of r will go like 1 by r square. Okay, P of r will go like 1 by r square. Now, classical energy, Okay, so which is basically obtained as classical energy is the average energy. Average energy. So that means this probability, that means average energy is what? Average energy is P of R into H nu. Of course, you may have to consider all the news that you are getting. So P of R H. Because P of R is going like 1 by R square, the average energy goes like 1 by R square. So classically, the energy observed is going like 1 by R square is reconciled with the average energy going like 1 by R square. And he used this idea of the probability is goes like 1 by R square. So it is sometimes you might have seen in some popular textbooks, it is written that Einstein was completely against the use of probability in quantum mechanics. Okay, so it is partly true, but he is the first person who introduced the idea of probability into quantum mechanics. Okay, and if you read the Nobel lecture of Max Born, when he got Nobel Prize, he gave a Nobel lecture. In that, he says that he was motivated by Einstein's way of introducing probability into quantum mechanics, and that is how he introduced the probability concept into quantum mechanics. So, so Max Born. Let's come back to Max Born. So Max Born had suggested that. So we were struggling with this question of what this psi represents. So he introduced a new concept, and he called this as, so psi, we don't know what this represents, but mod square of psi, okay, that is equal to psi star of x comma t into psi of x comma t. Okay. So this represents what is called a probability wave. Okay, so if you understand probability and wave separately, then also understanding what is a probability wave is difficult. So the probability wave essentially means that your psi star of x comma t into psi of x comma t multiplied by some dx has the following interpretation. This is probability that the particle is present or located between x and x plus dx at time. Okay, so it is the probability that the particle is located between x and x plus dx at time. So there is a concrete proposal by Max Born that the psi of x, this wave function, psi of x comma t, this is called wave function. And this is also called probability amplitude, because its square is called probability. This is called probability amplitude. Okay, wave function, and this is also called probability amplitude. And the interpretation that if you solve Schrödinger equation for some system, you get your psi, then what can you do with the psi? You can only determine the probabilities of different outcomes. So this is in some sense this completion of the story of what this psi is all about. Okay, so it is a kind of a probability that it will describe. And now the question is, what do you mean by a probability wave, and how to understand this? Okay, these are not important to make progress. As I told you, you can ask those questions and get some kind of a, you can sit down in one corner of the room and imagine this is what must be happening, that is what must be happening. And if there is no way of testing whatever you imagine, it is not worth testing. At least that is the argument which everybody worth imagining. That is the argument which everybody settles to in the quantum mechanics. Okay, so yeah, so this is in some sense the description of Schrödinger equation, and then the the meaning of the wave function. Okay, so any questions?
Sir, as we are describing a free particle as a plane wave, and a plane wave can travel from minus infinity to infinity. So free particle can also travel from minus infinity to infinity. Is it a right description?
Travel from means what? You are talking about minus infinity to plus infinity in space or in time? So minus infinity to plus infinity in x, that's what you meant.
Space.
In x, right? So that is what you meant.
Yes.
Yeah.
Yes.
So it can travel, right? So there is no problem. The whole space is available for it to travel.
Okay, sir.
Hello, sir.
Yeah.
Sir, in quantum mechanics, in question phase, I saw that in many cases they are taking non-interacting particles. And what is the difference between a non-interacting and interacting particles?
So whenever you have large number of particles, okay, whenever you have more than one particle, not necessarily large, if you consider interactions, okay, if you consider interactions, then it is difficult to solve Schrödinger equation. There are no mathematical techniques to solve Schrödinger equation for interacting systems. Because of that, they will consider non-interacting system, okay, and try to put in the interactions as an approximate, through some approximate technique. Okay.
Okay.
And how do we know whether this approximation is correct or sufficient? You have to only appeal to experiments. So if your results that you are getting approximate by using approximate methods like perturbation theory or variational principle, WKB approximation, like that, if your results obtained through these approximate techniques are matching with the experiments, then you are happy. If they are not matching with the experiment, then you have to introduce other techniques. Okay, so it is a game which is played by constantly coming back to experiment.
Okay, sir. If the particles interact, it will affect the potential, right?
Correct. So
okay.
the interactions between two particles will become an interaction potential.
So we will find difficult to find the potential increase.
No, you can find the potential. That's not difficult. If you put in the potential, then solving Schrödinger equation becomes difficult.
Okay, sir. And one more question, sir.
Yeah.
So actually, what is the dispersion and non-dispersion? And by looking some equations, if it is linear or non-linear, can we comment on whether it is dispersion or non-dispersive?
Basically, dispersion means what? Just like what you see when you pass through when a white light is passing through a prism, then it will spread, right? So
Uh,
dispersion is essentially that spread.
due
That is
to change
essentially
in refractive index.
refractive index is not change. It is basically different colors will travel with different speeds.
So can we
Correct.
take into account the phase velocity, group velocity, such things?
So it is uh, group velocity will come a little later because we are now talking about only one wave, right? So whatever is the velocity of this wave is called wave velocity, or later we will call this as phase velocity. Okay.
Okay,
So
sir.
even with this, we have, I mean, in case you have many frequencies, okay, so the frequency and wave number will have this relation, this dispersion relation. Okay, the dispersion meaning is same as what you have studied in your optics course. That is a spread of the different wavelengths into different velocities.
Sir, if we are given a set of equations
Mhm.
and some equations are linear, some are not, and
Hmm.
can we comment whether they are dispersive or non-dispersive by looking the linearity or non-linearity?
No, it doesn't depend on whether it is linear or non-linear. Okay, so basically a certain equation will have. Let's assume that you are always considering a plane wave. Okay,
Okay,
and then take different equations and you put in this plane wave and then look at what are the dispersion relations. Okay, so depending on your equation, you will get a different dispersion relation.
okay,
So
sir.
whether it is linear, non-linear, it doesn't matter. So what is the dispersion relation that you are looking for depends on the physics of the situation. Like here, for a quantum particle, I am looking for a dispersion relation where omega is proportional to k square. In some other context, you may have a different dispersion relation as the physics demands in that situation.
Okay, sir. Okay, sir. Thank you. It's very clear.
Yeah,
Excuse me, sir.
yeah.
So, like when we were talking of the wave in and defining it classically, then we write a equation for plane wave equation. So, I want to understand, sir, what does that, what we interpret from the plane? Like, is it a kind of real plane or complex plane?
So it is the plane corresponding to the constant phase. Okay, that means, for example, let's say that when you have a wave, okay, a particular distance from, let's say, origin, let's imagine at some particular time a point at the origin, okay, x equal to 0, t equal to 0 is 0, let's say. Okay, now that point, uh, h- how far is it traveling or how fast is it traveling along the way? Okay, so that is what is given. So that means if you say that at that point you have 0, that means there will be that 0 will happen at some other point also, right? So all those constant phase, the locus of points with the constant phase, because you remember this is a function of x and t, right? Suppose if you fix t, now this will be only a function of x, correct? Now all those values of x for which kx is equal to constant, okay, kx is equal to, or k dot r is equal to constant. K dot r equal to constant is the equation of a plane mathematically, right? So it is basically constant. Basically, the plane wave is more suited for three-dimensional thing because e to the power I k dot r is like k dot r equal to constant is like a phase in x y z. Okay, you ask all those questions, which are the x y z such that k dot r equal to constant is actually a plane, and that plane actually travels in a line. I mean, in the direction with the velocity omega by k.
Hello.
Yeah.
So I have another question, sir.
Yeah.
So like we had earlier defined wave equation classically, and then in order to define the dispersion relation, we define another wave equation for quantum mechanics.
Yeah.
So, sir, can I say that the what we defined classically was essentially wrong, or like? But then if I say this is a wrong equation, then why still it is applicable in the some cases? So can I interpret, okay, there is some fundamental limit to which this classical wave equation will work, and after that the classical wave equation is not working?
It's not wrong. What I'm saying is that the classical wave equation is not a suitable wave equation for these particle waves. Okay. The reason why we, especially if the particles are under the non-relativistic case, because under non-relativistic case, the wave equation is not giving the required relation between omega and k. Okay. But this wave equation with some slight modification is also the correct wave equation when you go to relativistic particles. Okay, even in quantum mechanics, when you go to relativistic quantum mechanics, in fact, Schrödinger had first written down that equation. But since he did not find that equation is valid for non-relativistic cases, he simply ignored that and then constructed a new equation. But then later people found that that is a correct equation, and that equation is now called Klein-Gordon equation. So Klein-Gordon equation is actually like wave equation only for a relativistic particle, because relativistic particles you can see E square is P square C square like that. So both are squares. So omega proportional to k dispersion relation is a good dispersion relation for relativistic particles. For non-relativistic quantum mechanics, it turns out that this is not the correct equation. So you want to describe non-relativistically a particle as a wave, and wave equation is not the correct equation to describe. And that is why you have to now write down the Schrödinger equation. But you take electromagnetic waves or waves on a string or any other waves that we are familiar with classically, they all are solutions of this wave equation. But this de Broglie waves or particle waves or matter waves that we are talking about, they are not of that kind. So you require a different equation to describe these waves.
Okay, sir, I understood this part. So then, sir, what make matter waves more distinguished? All I can understand is like in order to derive the dispersion relation, we got that wave equation, that quantum mechanics. But still,
Correct.
what make it fundamentally more different from other waves?
I mean, I have to answer this question slightly with some kind of a, I mean, it's not a very concrete answer. I am trying to say that at the first place, this wave itself is, it could be a metaphor in the sense, I don't know what it is, but now I want to use some language to describe. So maybe I'm using this language called wave, but it may not be a wave at all. You follow, no? So if it is not a wave at all, then talking that it's a different wave or something is but now you may say that, okay, last 100 years we have been calling it a wave. If it is not a wave, what else it is? So in my understanding, this wave is just a metaphorical representation, in the sense that we have to use some language, so we use this language. So we should not take it very seriously that it is like electromagnetic wave, or is it a transverse wave or longitudinal wave. So it is a wave is itself a kind of a colloquial metaphor, in my opinion. So it is like that. So we don't know. Okay, so you say it is a wave, then you say it is. If you read books on quantum mechanics, some people say it is a probability wave, some people say it is a probability fluid. What do you mean by probability fluid? We know fluid, but what do you mean by probability fluid? These are all some kind of a language use of language. More confusion will come because of this than the clarity. But I believe that we don't have to really worry about this question much, because what is unmistakably well developed and answers all of your questions is mathematics. And if you can say that, okay, I'm going to represent this wave by this wave function, and this wave function, I can get this wave function by solving Schrödinger equation for a given potential, that solves all your problems. Okay. Now you want to call it a wave, or you want to call it a fluid, you want to call it something else, it's up to you. But the final result is independent of whatever you want to call it.
Okay, sir. I got this idea too. So I have one more question.
Yeah.
So we had associated this matter wave, so-called matter wave, for a particle when it is moving, and we have developed a mechanism for that, like how we will describe it mathematically. So,
Yeah.
sirs, I just want to know, with the same mechanism, how we will describe in the same quantum particle is in stationary. Like, can we describe a stationary electron with the same matter wave concept which we had developed?
There is a little bit of self contradiction in this, in the sense that we will show. I mean, you already know, probably from your course on quantum mechanics, that there is nothing like any quantum particle stationary. Correct? So, by definition, there is a more fundamental principle called uncertainty principle, which will not allow any particle to be at rest. Okay? So, such a question does not arise, because every particle has to be jiggling around, it has to be moving around, it cannot be at rest. Okay, if you want to be at rest, you have to be running very fast. That is what it is.
Okay, sir. Okay, sir. I understood. Thank you,
Yeah.
sir.
Yeah. Any other question?
Sir, I have another question, sir.
Yeah.
Sir, we have seen that every physical observable is related to an operator in quantum mechanics.
Yeah.
But sir, there is no operators for time in quantum mechanics. Can we say that time is not a physical observable?
See, time always enjoys a different status in physics. I mean, even in classical physics, time is an underlying independent parameter always. Correct? I think starting from Galileo, Galileo probably was the first who introduced time as an independent variable to describe motion. And time is always an independent variable. So, in the same way, in quantum mechanics also, time and energy, they are treated as just parameters. Okay, how much energy and how time changes, these are just treated as parameters. So they are not observables in the sense of other observables. Okay, but they are physical. Okay? They are physical, but they are not. So they enjoy the same status what we give them in classical physics. So it's a parameter.
So we don't need an operator for time.
Yes. In the
Okay, sir.
formalism of quantum mechanics, we don't need time operator. There is no operator for time, and there is no operator for energy. Even though
Sir,
operator correspondence, I said E is like IH cross dou by dou t. It's not. It's not that the energy is an operator. It is just a correspondence. That means it's a mathematical, from a physical equation like E equal to p square by 2m. How do I get a mathematical partial differential equation? So this is a scheme to get the equation from that equation, but doesn't mean that energy is an operator.
yes, sir. Sir, another question.
Yeah.
Sir, according to uncertainty principle, if particle momentum is known, it can be in many places at the same time.
Hmm.
And similarly, from energy time uncertainty, if we know energy accurately, then if the particle is in many times at the same place.
Yes. Okay, energy time uncertainty is something which we require to discuss in more detail. Okay, so but essentially we understand that if the energy is, if we know energy precisely, that means it cannot be known precisely if you observe it for some small time. So in that sense, it is okay. But again, as I told you, that energy time uncertainty has to be understood differently than the position momentum uncertainty. But we will spend a little time on that.
Okay, sir. Thank you.